Okay, so in the last Instagram post that I made, we were looking at this really interesting project. This is Sierra Allende Ranch by Fabián M. Escalante Architects. Now, this project has a lot of really interesting design conditions, and I definitely encourage you to check this out by yourself. A lot of cool things going on here, but we were looking at specifically this wood screen, which looks like it might be at sort of the formal entrance of the design of the property. And the reason we're looking at that is because it kind of looks like it could benefit from some parametric strategy. I would say this definitely wasn't parametrically designed. This looks like it was done by hand, which is super cool because it gives it this sort of rustic, rough finish to it, which totally fits in with the overall project. So I'm not necessarily saying that this needed to be parametrically designed. I'm just doing it because of the exercise, the opportunity that we have to kind of exercise our brain and think about how this would be done parametrically. So let's sort of get into it. First of all, first we have to analyze what we have going on here, how this works as a system, how this works as a design. And then we'll just briefly kind of look at Grasshopper. Now, this video is not going to be an in-depth tutorial. This script kind of turned out to be pretty complicated, and I have to kind of prioritize my time. I have got a lot of other interesting projects coming down the line that I'm working on, so I have to pick and choose, which ones are most important. But if you guys are interested in an in-depth tutorial on this, please let me know, and maybe we'll be able to make that happen soon. So, anyways. What's the foundation of this system? Well, we have a primary grid. If you can see here, we have this diamond grid, and it's very consistent coming across the whole screen. You can always see the primary grid. And then we have these partial pieces. Some of them are full length going through the cells of this grid, full length, full length, full length. But then some of them are partial, and they kind of meet with the full length pieces. So that's sort of the foundation of it, right? So we have a full length, and then we have a partial and a partial. The full length is like the dominant, and then we have the partial pieces that are meeting them. So that's the foundation of how this works. And then we have a gradient going across, so it becomes very dense over here near the doorway, which is really, really cool. And yeah, so here you can see the doorway, and here you can see how you can really see that density changing, that gradient changing the density, right? So let's just hop into Rhino and take a look at how this could be modeled parametrically. Again, it's just going to be an overview of the script, and we're not going to go in depth. I'll just point out basically how this is working. So first of all, I've ordered my script into different groups. These groups are kind of defining roughly the sequence of how this script is working. And before I, start talking about how this thing works, let's take a look at some of the parameters and how we can modify this design now that we have a parametric system. So we have an overall length, and this could be, I could modify this so that the parameters work differently, but this is what we have so far. I have an overall length. I have a density. I have the number of units in the x-axis, and a number of units, number of cells in the z-axis. So we can, I can make this longer, and if I make it longer, it's going to stretch out those cells because the cells have stayed consistent. So what if I add more cells? What if I want to make this like a lot denser? It will take a little bit longer to calculate because we have more cells, and now it's really short because I haven't changed the number of cells in the z-axis. So what if I want to make like a giant screen? So I've made it 20 units in the X and 20 units in the Z. So it's going to be significantly taller. Wow. So now we have this giant wood screen, and it's still random. Okay, that's massive. That's pretty cool, right? So let's make it a little bit shorter again and look at some of the graph mapping capabilities. Okay, so we've brought it back down to I think roughly the dimensions of the original design, and let's just take one moment to look at some of the, how we're mapping the gradient. Well, we're using this graph mapper to map the gradient, and if we want to modify that, there's a few things we could do. We could make this, first of all, we're using the jitter component to kind of change how consistent the gradient is. As you can see, we have some somewhat empty, almost empty cells here, and then it becomes more dense, but we can see some like really dense cells showing up that are almost close to the middle. We can also see some cells with only 2 units that are very close to the side. So the density is kind of being shuffled around, right? And we're using the jitter component to do that. So if we took away the jitter, you would see that the gradient is a little bit more consistent. You can see that it becomes more consistently dense going across. Now you can also see that the density doesn't change very much going from about this side, the left side, to the center, and then it starts changing. And that's because we're using an exponential kind of relationship with this graph mapper, and we could change that by making it linear. It would have a more linear gradient. That's something that we could do. So now you can see that it's becoming more consistently, it's becoming more dense coming across the design. So that's an option that we have. I don't think it looks as good. I don't think it fits this product as well because the density is kind of really accentuating the entrance. The density gradient is sort of accentuating the entrance. So I think it makes sense to be using some type of exponential relationship. That was a little bit too harsh, I think. There, something like that. I like that. So those are the main parameters. We have some other parameters that are in this script, but they're less important. Let's just talk about, roughly how this script is working. Okay. So first of all, we have this first. Well, I talked about. No, I didn't talk about this yet. So basically, this group down here, this is just defining the concrete foundation, the I-beam that's coming across, and sort of these columns. I'm not sure if you'd call them columns, but these columns that are coming down on the edges, right? And now I should note that this did not need to be modeled in Grasshopper. This definitely could have been modeled in Rhino, and then the Grasshopper script could have conformed to that model. That's definitely an option. And if this was a project that I had to do, I might choose to do that instead, but I'm modeling it in Grasshopper just for the sake of the brain exercise. I like to model as much as possible in Grasshopper just to make it as hard as possible, just to get my brain working and just to go through these exercises, as much as possible. So again, this did not need to be modeled in Grasshopper, but I did it anyways just for fun, right? And so that's what this group is doing. It's just taking care of the non-wood portions of this model, the steel and the concrete. Okay, so moving over to the next group, this group here is defining just the basics of the grid. So let's turn off the final result and let's look at how this grid is working. Well, basically it's going to show up here, and as you can see, when we change any of these parameters, our edge condition is always going to work out perfectly. It's always going to split it perfectly at the edges, okay? And if you go back and you look at how we change those parameters, when we change the parameters, these edge conditions always worked out perfectly because we set up the script accordingly, right? And so how this is working is we're basically taking a square grid. First of all, we're grabbing both the vertex points and the center points, and we're using that to define the cells of this diamond grid, or it's a square grid rotated at 45 degrees basically. So from those points, we're taking some planes, rotating those planes 45 degrees, and we're placing our rectangles, but they're squares, right? And so that's how we're basically creating this grid. And from there, let's see, what are we doing? We're gonna build one solid grid right here, one solid cell, I should say. Now the cell is basically an extruded rectangle frame, but then I chopped the corners off with a Boolean difference component. Because as you can see, if you look in the picture, it kind of looks like the corners are filled with like mortar or something. I don't know. I can't really figure out how this detail works, but it doesn't look like it doesn't look like we have full length pieces of wood. It looks like we have single pieces of wood that are being joined in the corners somehow. Not exactly sure how that corner detail works or how that intersection detail works, but something's going on there. So what I just did is I modeled separate pieces of wood to make it look like the original piece. So we have these separate pieces of wood. So I took a frame like this, and I chopped the corners off. And instead of modeling the entire grid and then chopping the corners off of the entire grid, which would take a lot longer to calculate, I just did it once, and then I used the orient component to place them along the entire grid. So that's obviously the foundation of our wood screen. And now let's talk about the more complicated part where we're dealing with the density gradient, the partial pieces inside the cells of this grid, right? So the way we're doing this is we're using a graph mapper, as we looked at before, to map the density change going from left to right. And right now we're using the Bezier curve modifier, and we have this kind of exponential shape. And the density of the pieces right now is going from 1 to 50 from 1 on the left to 50 on the right, but a lot of those pieces get culled out, so we're not going to actually end up with 50 pieces. A lot of them get culled out by the end of the script. We're using the jitter component to kind of shake it up a little bit so it's not fully consistent as we looked at previously. Let me turn that off. And so then we're just basically, I'm going to skip over a bunch of parts of this, but basically we're using some vectors to what we're doing is we're taking some of the sides of the diamond grid. We're selecting some of the sides randomly, okay, and then we're moving them into the cell. So we're using some vectors to move them into the cell at random distances. So we randomize the distance of them. I think it should be like this. Yeah, there we go. So we're taking a side, and then we're like right here, we're taking this side, we're moving it in at a randomly generated vector length. We're taking this side, we're moving it here. You can see the arrows, right? You can see these vector displays. And so all these vector displays are indicating moving one of the sides of the cells into the cell itself by the defined length of this vector. Okay, but we're obviously leaving the sides for the main grid, but we're kind of duplicating it to create these center component, the center portions, these center the parts that are inside each cell, right? And then we're using duplicate lines so that we don't have any wood that's overlapping, because wood has thickness. The thickness is like around 38 millimeters, or 1.5 inches, because it looks like we're using 2x6s or something like that. And so we're using a remove duplicate lines for any line that's closer than 30 millimeters. One of those lines will be removed. So we're taking out a lot of them in this area where it's very, very dense. We're taking out a lot of them with remove duplicate lines. Super useful component, right? So that's what this group is doing. We're ending up with something that looks like this, right? So those are our partial pieces, and this is after let's look at what it would look like before the remove duplicates. This is what it looks like before remove duplicates, and then this is what we're left with. So you can see a lot of them are closer than 30 millimeters in this area, so they're being removed. Super, super useful. So that's what we're coming out of here. Now, we use a dispatch component to split this list up into A and B. We're using a true-false pattern, so it's an equal length list in A and B. Well, roughly equal. And the reason we're doing that is because if you look closely, you can see there's actually 2 depths. So our main grid is like a 2 by 12. It looks like a 2 by 12, maybe, or a 2 by 10. But you can see the partial pieces, the pieces inside. Look at this one. It's in front, and this one's in the back. So we actually have 2 depths. See, these ones are in the front, and this one is in the back. This one's in the front. This one's in the back. This is in the. Covers the full one. I didn't do that for any of them, but this one's in the front. This one's in the back. So there's 2 depths. So what I'm doing is I'm breaking it up. I'm splitting it into 2 lists. Okay, and then I'm doing a script that splits a bunch of these pieces, so we get these partial pieces, and I'm doing that like twice in parallel. So we just have 2 totally separate kind of scripts for a portion of this that creates 2 totally different screens, kind of in the front and the back. That's kind of the process here. So you can see this portion of the script is 2 portions of it that are completely identical. Now, this could have been done using grafting techniques. I've done stuff like that before, but I didn't want to go. It would have taken a lot longer. So if there were like 10 depths, I definitely wouldn't duplicate this 10 times. I would figure out how to do this using some type of data management strategy. But in this case, we only have 2 of them, so I figured I'll just duplicate the script. And so what we're doing is we're finding intersection points between the different parts of the we're finding the intersection points between between these partial pieces. And what I've done is I basically set up like a primary piece and then the secondary pieces that will be split. That's kind of the basics. So so each cell gets a primary piece randomly selected, and then the secondary pieces that are left over. So basically, like I said, we have a primary piece, and then we have our secondary piece that gets split, right? So a primary piece, there's only one. A primary piece, our secondary pieces get split. So that's kind of like the idea of how this works, right? So between our primary piece and our secondary piece, we find the intersection point. We do a whole bunch of data management that I'm not going to get into, but I would talk about if this is something that's interesting. So let me know. And then we shatter those curves with the shatter component. So using our intersection points, we shatter those components, which basically means that we're splitting our curves. And then once we split it, we still have the entire curve, but it's been split into 2 or more than 2. And so then at that point, we're just we're using the random component to select one side or the other. So the random component is just producing 1 or 0 for each curve. So it's selecting 1/2 of it. So you can see here. So look at this. If we look at one cell, we have our full curves, but they're shattered, and then we choose one side or the other. So this side, this side, this side. And that's how we're ending up with these partial pieces. And that's how we end up with, I think you should see this one and this one. So now we have our primaries and our secondaries that have been split, right? So our primaries and the secondaries. And let's turn on our grid so you can see that in context. Right? So here's our grid and our primary pieces like this one, and then our secondaries like this one, this one, this one, right? So that's the foundation of how this gradient works. And like we said, we use the graph mapper to change how many curves were duplicated into the cell, and that's how we're creating the density difference. So you can already see the density gradient taking place here with just the curves. So like I said, we've done this twice. We've done it this time, and we've done the exact same thing this time, but I've moved it back to different depth, right? So we've done the same thing, but we're using different random values, of course, and different depths. And so we end up with something like this, right? Really interesting look already, but you can see we have different depths. Okay, and then we're using extend curve so that we don't have any overlapping portions. We have our joints are working, you know what I mean? and we're offsetting it to create something with a thickness, and lofting it to create surfaces, and then we're extruding it to create pieces of wood, right? And then we're using solid intersect to only keep what's inside the frame. There we go. And then over here, we're just using V-Ray to create those renderings, which is something I'm not going to talk about in this video, but I can definitely talk about it. I'm just trying to, again, I'm trying to prioritize. So that's the last thing we're doing. We're using solid intersection to define, to maintain, to keep everything that's inside the frame. And so so this whole thing, this is kind of the fundamentals of how this script works. If you have any specific questions, I'm always happy to answer. Let me know in the comments or shoot me a DM. So I hope you found this video helpful. Again, didn't go in depth. I had to skip over a lot of things, but if you are interested in a more in-depth tutorial, please let me know and I might be able to make something happen. But for now, I hope you enjoyed. I hope you designed something awesome today, and take care.